So, do you know what your system is doing while you're not looking? Does it behave as expected? Are its real-time requirements met? And does it produce correct results? Today, let's explore how we can gain more insights into the system through the debugger and how a clever chip design can help us to make that easier. My name is Johannes Lask. I'm software developer, product manager, and embedded expert at Sega Microcontroller. And while we develop embedded software and middleware components, you might know us for our J-Link debug probes. So with the J-Link and its tools, we are continuously improving and evolving its feature set. And we research and develop solutions to help our users to make debugging embedded systems a lot easier. Today, we'll have a look at one of those, at different options of how a debug probe can help access memory in RISC-V devices. We'll see the possibilities these options offer, and ultimately we'll explore the tools which provide you deep insight into a system through memory access. So let's start with a bit of background of how debugging is enabled on RISC-V. We're talking about the specification for RISC-V external debug support, the de facto standard for native debugging. And we're debugging with a regular debug probe through the standard JTAG debug transport module. Or to be more precise, the probe goes through the JTAG tab and the DTM to use the debug module interface to talk to the debug module. And then the debug module is connected to the RISC-V cores or hearts in a multi-core system. So at that level, what do we need to do for debugging a system? We need to reset, halt, and resume hearts. We want to get status information from the device. We want to read and write general purpose registers, CSRs, and other registers, and we want to access memory. So the concrete implementation of all those operations is up to the chip design, but the external debug specification describes the expected behavior. And we'll have a look at reading and writing memory in this talk, and this can be achieved and implemented in different ways. So the first option is to use the abstract access command to read registers. This is already required because that's how the debugger can read general purpose registers and usually also other registers through the probe. So as an addition, to provide more functionality, it can trigger execution of the program buffer. The program buffer is a small region from which a core can execute instructions, and the debugger can control the instructions in the program buffer, and with that, let the core perform all kinds of operations. For example, to read memory, the debugger writes a load instruction into the program buffer, sets a register to the address to read, and reads back the result of the executed instruction. And likewise, to write memory, the debugger writes a store instruction into a program buffer, sets one register to the address to write to, and another register to the data to write. Another option to read and write memory is the access memory command. When this command is implemented, it enables direct access to memory with the core's view, and the debugger does not need to access registers and the program buffer anymore, which produces a lot smaller overhead and is more efficient. But both of these commands access memory by involving the core and its components in some way, and this can be used to see the memory with the core's view. But usually it requires it to be halted and in debug state. An alternative to that is the system bus access block. And the system bus access provides a direct connection to memory without involving the core anymore. It can, for example, be another bus master similar to a DMA, and the debugger can read and write memory through it even while the core is running. So in comparison, all three options have advantages and use cases. Accessing memory through the program buffer and access memory command provides the same view and privileges as the core would have, and such access, for example, would respect caches and virtual addressing. System bus access instead uses physical addressing. It has full access to all memory in the system, but its view might not be coherent with the core's view if, for example, caches are involved. The access memory command and system bus access have less overhead and can increase debugger's throughput. This may, for example, be useful and noticeable not only for programming a device, but also when scrolling in a debugger through the memory window. And system bus access can have full access even when the core is in fault state. With that, system bus access can read and write memory while the core is running and with almost no interference with it. So now we know how memory can be accessed on a RISC-V device, which debugging features can be enabled with that. Standard operation in a debugger, of course, is inspecting symbol values while the target is halted, and this is available with all three access methods and usually done using the program buffer, as it is implemented most of the time and it has core view into memory. But most debuggers also offer watching symbols and periodically updating them while the target is running. This is usually done using system bus access, because the other options need to temporarily halt the system, which impacts real-time behavior and execution. And since system bus access is almost non-intrusive, memory can be read at higher frequencies without interfering with the core. Now, our J-Link debug probes feature high-speed sampling, so symbols can automatically be read at frequencies up to around 100 kilohertz. And this provides runtime system insight to variables and states by tracking values over time. System bus access also enables the use of Sega real-time transfer. RTT is our invention and contribution to efficient embedded debugging. It is most commonly used, for example, for debug printf logging, but can moreover transfer any kind of data from a debug target at up to around 3 megabytes per second. And this is done via memory access only. Puts fewest additional load onto your CPU, so in code it's barely more than a memcopy call, and it eliminates the need to add an additional serial port or similar to a hardware just for debugging purpose. So with J-Link, all that becomes available on the standard debug interface. Last but not least, the most powerful tool we get with system bus access and RTT is System View, real-time recording and visualization tool to analyze and profile the behavior of embedded software. It's ideal for complex systems with multiple threads, tasks, and interrupts, and provides insights into runtime performance. System View works by instrumentation of an underlying RTOS and the application of the firmware itself. It generates events to provide a system-level trace and records it via RTT. With J-Link, we can capture the events, analyze and visualize them, updating live all while the target system is running. So how can System View help to gain system insights? With instrumentation of the RTOS or scheduler or of interrupt service routines, System View provides timing information about all contexts in a system, and it supports you to measure the runtime of tasks and interrupts, and can be used to verify the real-time requirements and constraints are actually met. The visualization of communication and influence between contexts helps to find inefficiencies and problems which are hard to analyze with traditional debuggers. System View provides analysis of the CPU load to profile a system. It helps to see how much computing power is actually needed or where execution might need to be optimized. And with System View, developers can further instrument their application, so you can use it to add debug log output, record runtime of APIs and functions, or to set markers and specific events of the system to count and measure timing. So similar to high-speed sampling, System View can also be used to record data samples. And these samples are plotted and visualized in the timeline along contexts, which provide more details about what's happening there. Checking runtime memory usage is usually also not an easy operation with a debugger. And System View features heap and stack monitoring, which makes this simple. For each task, the stack usage can be recorded over time, which helps to get a better estimate of how much stack a system actually needs. And we can also instrument a heap implementation to visualize and analyze dynamic memory use. So there's a lot more we can do with System View. And if you're interested, feel free to stop by at our booth outside during the break for a live demo. And finally, System Bus Access is an optional feature of RISC-V debug implementation. It does not add much complexity to a chip design, but it can provide real advantages for embedded software engineers. And if you're designing chips or work with a silicon vendor, we encourage you to think about adding it to your design. If you're already using custom or off-the-shelf RISC-V devices, check whether System Bus Access or maybe the memory access command is available and make real use of it. Thanks.